Section 4.4 is about discrete probability. So most counting problems are of the form, how many blanks have blank property? So more formally, this question is asking, how many elements of set U are in some subset A? Which is basically the same question as what percentage of elements in U are in the subset A? And the answer to this question is a ratio that can be thought of in terms of chance. What is the probability that a randomly chosen element of U is in the subset A? So all of these questions are basically the same idea, we're just thinking about them in a little bit different way. Suppose A is a subset of a non-empty finite set U. The probability that a randomly chosen element of U lies in A is the ratio, so probability of A is equal to the order of A divided by the order of U. So A is the subset, so it's the order or the number of elements in the subset divided by the number of elements in the whole set U. We call the set U the sample space, and the set A is called an event. So an example, if you roll two standard 6-sided dice, what is the probability that you roll an 8? Well, we have two dice, so let D1 be the set 1, 2, 3, 4, 5, 6, and D2 for dice or die 2, it also has sides 1, 2, 3, 4, 5, 6. So the sample space is the Cartesian product D1 cross D2, and these ordered pairs, they'll be like 1, 1, 1, 2, all the way up through 6, 6, represent all the different possibilities of rolling two dice. So we could roll a 1 and a 1, we could roll a 1 and a 2, or we could roll a 2 and a 1. And those two things are different because we're designating one dice as die 1 and one as die 2. So 1, 2 is different than 2, 1. So the order of this sample space is 36. Remember, the order of a Cartesian product is the order of D1 times the order of D2. So 6 times 6 gives us a sample space of size 36. The event would be the subset whose coordinates add to be 8. So we can't pair 1 with anything because there's not a side of 7. So our smallest one we could get is 2. We could have 2 and a 6 giving us 8, 3 and 5 giving 8, 4 and 4 giving 8, 5 and 3, and 6 and 2. So the order of the event is just those 5 options. The probability then of such a roll is 5 out of 36, and if you type that in the calculator, it's 0.139. Probabilities are usually given in fraction or decimal form, but you can also think of them as there's a 13.9% chance that you roll a sum of 8. So we have another theorem. Let A be a subset of a non-empty finite set U, and let A complement be the complement of A in U. If the probability of A is P, then the probability of A complement is equal to 1 minus P. This theorem helps us answer questions like this. If you roll two standard 6-sided dice, what is the probability of rolling 10 or less? So to approach this problem directly would take a long time. We would have to find the probability, well, we can't roll a 1, so the smallest we could roll is 2. So we could roll a 2 or a 3 or 4 or 5 or 6, all the way up to 10. We'd have to get all of those different cases and add up those probabilities. So it's easier to think about the complement. Instead of thinking about what's the probability of rolling 10 or less, think about the probability of rolling 11 or 12. So the probability of rolling 11 would be our first subset. The only options there are 5, 6, and 6, 5. And subset 2 would be the probability of rolling 12. There's only one case there, if we roll double sixes. So the total probability, subset 1 would be 2 choices out of 36, plus subset 2 is 1 choice out of 36. That gives us a total probability of 3 out of 36, or if you reduce, 1 out of 12. The theorem says that the probability of the complement is 1 minus this probability. So the final answer would be 1 minus 1/12, which is 11/12, or 0.917 if you prefer the decimal. The reason this works, if we think about these in terms of percentages, the answer here would show a 91.7% chance that this is true. Well, we know that percentages add up to 100%. So if we take 100% minus 91.7%, the complement would be everything left over. So that's essentially what we're doing here, but instead of percentages, we're working with fractions or decimals. So we're using 1 instead of 100%. Expected value. So far, we have seen examples where probability quantifies how likely an event is to occur. But probability can also be used to make predictions about a random variable. So a random variable is a numerical result of a random experiment or process. And the notation looks something like P of x equals 5. That represents the probability that the random variable x equals 5. You could also have something like P of 0 less than or equal to x less than or equal to 5. In English, that means the probability that the random variable x is between 0 and 5. So if we look at our example of rolling dice, rolling 2 standard 6-sided dice is a random experiment. I could pass out dice in class and have you roll them indefinitely, and that would be like you conducting an experiment. You could write down what your sums were, and the sums of the values on those 2 dice, that would be the random variable x. And every time you roll, you would get a different variable, and when we record those, we would just get different numbers throughout the class. We showed in a previous example that the probability that x equals 8, so that our sums added to be 8, was 5 out of 36. And we showed in a previous example that the probability the sums were less than or equal to 10. We showed that probability was 11 out of 12. Suppose that we repeat a random experiment several times and record the value of a random variable each time. If we averaged these results, we would get an estimate of the probabilistic average of the random variable. So let x1, x2, all the way through xn be all of the possible values of a random variable x. Then x's expected value, represented by e of x, is the sum x1 times the probability that the random variable is x1 plus x2 times the probability that your random variable is x2 plus all the way up to xn times the probability that your variable is xn. Let's make sense of this with an example. In the both ways version of Australia's Cash 3 lottery, you pick a 3-digit number from 000 to 999, and a randomly chosen winning 3-digit number is announced every evening at 5:55 p.m. You win $580 if your number matches exactly, and you win $80 if the digits match the digits of the winning number, but in a different order. What is the expected value of the amount of money you win? So first, let's find the order of the sample space. We need to choose 3 different numbers. So as we did in sections 4.1 and 4.2, we have 3 slots that we're trying to fill in, make a choice, and there are 10 digits to choose from. So we'll have 10 choices for our first number, 10 choices for our second number, 10 choices for our third number. So our sample space has order 1000. That means the probability of winning $580, you have to match that one number exactly. That's one choice out of the total 1000. The probability of winning $80 is 5 out of 1000 because the number of ways you can permute the 3 winning numbers would be 3 factorial, and we take away that one perfectly matched number. So for example, think about the winning number being 123. We can permute those numbers 6 different ways. You can write them down if you want to make sense of it. But if 123 is the winning number, then we would not win $80, we'd win $580 for that choice. But there are 5 other permutations that would give us $80. That's where that number is coming from. So the probability there is 5 out of 1000. That means there are 1000 minus 6, so 994 choices left. And if you choose any of those 994 choices, you win nothing. So the probability that you get $0 is 994 out of 1000. So we can calculate the expected value. We have X1 in this case is $580, and the probability of us winning $580 was 1 out of 1000. Plus $80 times the probability that we win $80 is 5 out of 1000. Plus $0 times the probability that we win $0, 994 out of 1000. If you type this into your calculator, you get a decimal answer, 0.98. That means your expected value, if you were to play this game over and over and average your results, then you can expect to average around 98 cents. Now, you don't get 98 cents ever. You either get nothing, or you get 80, or you get 580. But we're saying if you play this every day for years, on average, all the days where you get nothing, average with the day where you win the 80 or the $580, over time it averages to about 98 cents. So we will practice more of these kinds of questions in class.